poles, 6 pole, 3 phase 50 Hz 15 kilowatt induction motor drives a constant load torque. So he has given torque as constant at rated frequency, rated voltage and rated kilowatt output. Okay, speed is, let us take the speed is NR1, which is equal to 980 RPM, and an efficiency of 93%. Then the new operating speed, if there is a 10% drop in voltage, that means he has given a V2 as, I can write 0.9 times of V1, which is equal to 0.9 into 230 volts. Okay, and 5% drop in frequency. So F2 is equal to 5% drop. So this is 0.95 times of F1, 0.95 into 50 Hertz. Okay, so V2 is equal to 0.9 times of V1, that is 0.9 into 230. So this is 207 volts. F2 is equal to 0.95 into 50, so this is 47.5 Hertz. Okay, now for this change in voltage and frequency, we have to find the rotor speed. Okay, earlier it is 980 RPM, now we have to find the new speed for the changes in V2 and F2. Okay, now we know that slip is directly proportional to V square by F. Okay, now what is slip 1? Slip 1 is synchronous speed ns minus nr1 by ns. Okay, ns is given as 120 into f by p. So this is 120 into 50 by 6. Okay, we have a slip speed of 1000 rpm. So S1 is equal to 1000 minus NR1 is 980 divided by 1000, which is equal to 0.02. Now what is S2? S2 I can write from this relation. S2 is equal to S1 times of V1 by V2 whole square into F2 by F1. So this is equal to S1 is 0.02 into V1 by V2, so this is 230 by 0.9 into 230 whole square into F2 by F1, so this is 0.95 F1 by F1 whole square. From this you can find it as slip 2 is equal to 0.0234. Okay, so NR2 rotor speed 2 is equal to slip times of, that is synchronous speed times of 1 minus S2. Okay, synchronous speed ns is equal to 1000 rpm, so this is equal to 1 into 1 minus S2 is equal to, you will get around 928 rpm. That is option B as correct answer. Now the next question is, assume all losses are constant and new output power of the machine is. Okay, now output power is equal to, we can write tau into omega. Okay, since torque is constant, P is directly proportional to omega is equal to 2 pi n by 60. I can say that it is directly proportional to speed n in RPM. Okay, so P2 is equal to P1 times of N2 by N1. Okay, now this is equal to 15 times of N2 is 928, N1 is 980. So this is equal to 14.2 kilowatt. So option is C.
The angle modulated wave is given by Yc of t if the phase deviation of the angle modulated wave is. The maximum phase deviation is nothing but 50, that is this, the maximum value of this decides maximum phase deviation. So 10 plus 5 is the maximum phase deviation, that is 15. Option C is correct. The bandwidth occupied by the angle modulated signal is, see, omega I is nothing but omega C plus del F. So del F max is equals to omega I max minus omega C. So may fi that is equals to 1 by 2 pi d of dt 2 pi fct plus 10 sine 2000 pi t plus 5 sine 4000 pi t. Now if we differentiate, we will get it as fc plus 20,000 pi plus 20,000 pi. So delta f max is nothing but 40,000 pi divided by 2 pi, which is 20k. So f max is nothing but 2k. So bandwidth is nothing but 2 into delta f plus fm, that is 44 kilohertz. That is option A is correct. Closed loop control system for regulating the generator terminal voltage E0, which is shown in the figure. The forward path gain is 200 and the feedback factor is this 0.1. The reference voltage for keeping E0 to 50 volts. E0 is nothing but G by 1 plus GH into ER. Here this is 250, G is 200 divided by 200 into 1 by 10. So 200 by 21. So this is ER. ER is equals to now 21 by 200 into 250, which is equals to 26.25 volts. That is option C is correct. Percentage E change in E0 is equals to, here percentage change is this one, 200 divided by 20 ER minus 200, this is 180 new one, ER divided by 200 by 20, this is 21 ER. So if we calculate this one, we will get it as into 100, 0.526 percentage. That is option C is correct. Consider the following multiplexer where I0, I1, I2, I3 are data input lines given by selected by two address lines A1, A0 and EN is the enable input. For the multiplexer to do its function, first of all it has to be enabled. So if we write the truth table for that one, that is X, Y, Z, F, there are 8 combinations. So whenever for this particular input combinations, it's not going to work. The function is going to be 0 whenever Z is going to be 1. If Z is going to be 1, enable is going to be disabled, so the multiplexer is not going to do its function. So F is going to be 0. Whenever Z is equals to 0, it's going to be enabled. At that time this is 0, this is 0, this is 0, this is only the 1. So F is equals to XY Z bar is its output. That is option A is correct. The number of 2 input NAND gates required to implement the above function, that is X, Y, XYZ bar is equals to this is implemented X, Y, Z, so it requires 5 NAND gates to construct this function. This is XYZ bar, so option C is correct.